hungry, and you're eating in front of me. Okay, that's good. It's my fault I'm hungry. I'll give you a quarter for the rest of that sandwich. So here we are, Wednesday, the day before assessment number 9. Assessment 9 will be 80% on kidneys and liver and 20% who knows, right? How it works. I'm still doing assessment 8 grading, but the computer wasn't quite working perfect last week. Nothing about the questions, but it wasn't scrambling them like I wanted to. So did you notice there were a lot of A's? Answer A's, and I hope that didn't freak you out. Like, well, yeah, and I didn't say anything because I didn't want to like freak you guys out. But see, the computer program, if you push the right button, what it does is scramble all the questions and then scrambles all the elements in the question. And I could get it to scramble the questions, but I could never get it to scramble like the ABCD things like that. And you know how they update things for bugs and then somebody moves a button someplace. I couldn't find the right button to do that. So it came out with a lot of A's. I saw that and I'm going, I just can't say anything, you know what I mean? So the thing is, it's a good lesson. Don't say, oh, there wouldn't be that many A's in a row, or how come there's no E's? Because see, I don't really have control of that, right? I just push a button and it randomly alternates everything, scrambles, I should say. So, but I'm over half done, and there's a lot of, 48s, 50s. I think there was an extra question, so 52. So it looks good. Okay, so before I get into my stuff, I'm actually uploading yesterday's lecture up here right now. It's going to YouTube as I'm talking here, so that will be up there shortly. But questions about anything, the reading, the videos, anything we did yesterday? Yes.
Can you explain the difference between angiotensinogen and angiotensin?
Okay, right. Now angiotensinogen is made by this organ. Fill in the blank. What is it? It's a big protein found in the blood, and you should always guess this organ. Liver. Even if you don't know, guess liver. Some big protein floating around the blood. The liver makes everything, a lot of it. That's not going to be a 100% answer all the time. So angiotensinogen is inactive. It's inert. It doesn't do anything, but it's always there. It's floating around. And then, if renin is released, and where's renin coming from? Kidney. So if renin is released, why? Low blood pressure, right? Low blood pressure, and renin is released by the kidney. Now you've got the big protein out there, and you've got an enzyme that wants to work on it. So angiotensinogen is a substrate that goes to angiotensin 1 as a product. Remember, enzymes take a substrate, make a product. So angiotensinogen is inert, it's always floating around, and renin, if it is released, so renin is never around in the blood until it's released by the kidney. Then it converts to angiotensin 1, that's floating around in the blood, and as that molecule goes through the lungs convert it to angiotensin 2, which causes vasoconstriction of blood vessels. And if you have low blood pressure and you make all the pipes smaller, then blood pressure will go up. And in the lungs, what's the enzyme in the lungs that does this? That takes substrate angiotensin 1 to angiotensin 2, and what is it? ACE, angiotensin converting enzyme. That's my story. And see, you guys give me a quiz every day, don't you? Look at it. But that's okay. That's why we do face-to-face. It's you can't do things online that's perfect like this. You can do some things online, I mean, yeah. But. Okay, other questions? Yeah, and the kidney stuff, the video has that. Remember where it says, I think it's a diagram where there's a lot of arrows coming in and out, and things that go out are made by the kidney, things that come in. I gotta make one like that for the liver. So if anybody wants to remind me about that, Aaron, sometime, if you look at that kidney thing, I don't know if you've seen it, the kidney where there's a lot of things coming out in, I wanna do liver. That'd be kinda neat.
Can you clarify how ADH fits in with angiotensin?
Well, it's anti-diuretic hormone, right? That's coming from the posterior pituitary. And so that, when the brain basically senses like you need to conserve water, it releases ADH from the posterior pituitary, which is related to the hypothalamus, right? It's all kind of one tissue. And then that goes to the kidney, that's the target tissue. So like if you're making that hormone chart, you know, posterior pituitary, ADH, travels to the target tissue, which is the kidney, and anti-diuretic means stop making so much urine. And then if an animal or a person is giving, so this is a little sidebar now, if a person or an animal is given a diuretic, that tells the kidney to make more urine. So it's all about how the brain has sensors for osmolarity and all this stuff that we don't really talk about, but the brain is monitoring this.
Does it cause the release of renin?
Not really. The renin is more a low blood pressure directly on the kidney. Yeah, good questions. Excellent. Other questions? Here we go.
So you think it tells the kidney to water?
Yeah, make less urine. Anti-diuretic. ADH tells the kidney to not make so much urine.
Angiotensin's made by the liver, right?
Angiotensinogen.
Okay.
The O-gen is on the end. That's made by the liver.
I get
And then, so you can't really say angiotensin. You gotta say angiotensin 1, angiotensin 2. Okay, well let me show you a couple things that are dangling from yesterday, and it's the supernumerators, and show you a couple pictures, and then we'll go on to probably liver stuff. So yesterday I mentioned that be careful, sometimes there's more than one item, and so I'm just looking for maybe a good one here. Here's and so let me enlarge this a little bit. I won't dangle on this very long. But over here on the far right, the kidneys are up here. In this image, they're not really showing up very well. But you can see there's 2 ureters over here versus 1 there. Okay, so that other one would be called a supernumerary ureter. Supernumerary means more than the usual number. So if the usual number of something is 2 and you got 1 more, that's supernumerary. If the usual number of some organ is 1 and you have 2 of them, then you've got a supernumerary X, whatever it is. So then I have supernumerary kidneys here, and this one's an old one I've used a lot. So, and this shows you a nice diagram. I guess I'm thinking this is the aorta. I don't see the vein right now. So this would be the, let's say it is. So here's the renal artery. You know, there's like a million branches. But here's an extra kidney right here. Now the thing is, it's hard to tell from here where the ureters are. And I think they're not showing this. This is probably a blood vessel here. So like this kidney is getting its blood here. This kidney is over here. And then this kidney is over there. So that's a supernumerary kidney. Now the other thing is, we didn't talk about kidney transplants, but like if an animal or a person gets a kidney transplant, in one sense, it doesn't matter where you put it in the body. Because kidneys just filter blood, right? All it needs is an arterial supply and a venous supply and some place to put the urine. But usually what they do with kidney transplants, somebody that needs a kidney, if the 2 original ones, and they're gonna be low functioning, but as long as they're not diseased, they usually leave them. And that's a good strategy. So you've got these 2 kidneys that finally they're maybe down to 15% of their original capacity, and the person is having trouble. They'll put the extra kidney down low here in the pelvic cavity, hook it up to a blood vessel, and route a tube to the bladder. And then, remember this is a recipient now, I'm putting down here. The reason they leave the original two, as long as they're working somewhat, is if this transplanted kidney gets rejected, they can take it out and maybe look for another transplant. But what if they would have transplanted a kidney and then taken out the two original? Now you are SOL. That's sure out of luck, right? So it's a really good strategy. As long as they're not cancerous or, infected, they're just like operating at such a low capacity. Leave them. Because there's nothing magic about having a kidney right there. You wouldn't take that kidney out and put another one right there. It'd be nice, because you've got big blood vessel and everything. But put it down here, low, closer to the bladder, hook everything up, and then if it gets rejected, you can take it out and you've bought some time, because the two original ones are still going to be doing something.
So if someone had a kidney transplant and kidney was rejected, what would then happen?
Okay, that's a good question. So what if you get a kidney transplanted and it gets rejected by the recipient? If it's getting rejected by the recipient, and her question was, can you give that kidney now to somebody else? That might be a better match, right? There's this tissue matching. No, that kidney is damaged. Because it's being rejected, that means there's immune cells fighting it from the recipient. So you would never, that I can think of, transplant it to somebody else, because it's a damaged kidney. Good question, though. There might be one tiny little instance where they could, but you'd have to do like a little biopsy and see what histologically what's going on. But usually you'd have so many immune cells in it that are damaging it that it probably wouldn't be worth transplanting. Okay, well, that's supernumerary. Now the next thing I wanted to do was, like yesterday, I started out by going through some of the reading. And I want to do that again. There's those things uploading. So let me go to the reading. And yesterday, how many clicks did we do? I know we did just the first one, I think. Let me do the second one here. Yeah, question?
Just like autoimmune cells, what are you doing?
Well, okay, if the kidney is being rejected by the recipient, right, the person that got the kidney, there's immune cells damaging the kidney. Yeah, it's because it's going to think of it as non-self, right? There's this whole thing about self versus non-self. And so it's going to be viewed as foreign to such a degree that's damaging it. And they'd have to remove it. So I'm almost 100% there'd be no cases where you could transplant. Okay, so this reading, I just want to go through some of the terminology. Talks about renal abnormalities. Of course, renal means kidney. There's a gland near the kidney. And what's that gland called? Adrenal. So you add AD in front of this, right? The AD prefix means nearby. So look at, you've got the renal gland and you've got the adrenal gland. Pretty funky. So dysplasia, plasia means growth, so dys means abnormal or, so not normal growth. Okay.
Kind of a little bit off topic.
Sure.
Why do so many ferrets have adrenal gland issues? Like, what about them makes it?
Right, yeah. That's a little sidebar, but since we mentioned adrenal glands, yeah, they do have, ferrets have a lot of adrenal gland problems. I think one of my students in another class gave a presentation. I want to say a third or a half, if they live long enough, something like that, will have this adrenal. I don't know if it's something in the genetic makeup of all the ferrets. I don't know. I don't know the genetics of the breeding. How many ferrets are breeding out there? If you get a small population, and they're all coming from this one population, you could have a genetic cause for the adrenal problems. I don't know. You'd have to look that up. But yeah, they have somehow. They always have. They run into a lot of adrenal problems. I don't know. It'd be interesting to find that out. I don't know. Good question. Okay, so plasia is growth. So this would be abnormal growth, and hypo means low growth, right? So you could have very small kidneys. That brings up an interesting point. And it's just another thing about kidney growth. So everybody usually is born with 2 kidneys, okay? Now there's people walking around maybe with one and they don't know it, right? Unless something happens, a lot of times these things go undiscovered, right? But let's say you have two kidneys and you're 10 years old. We'll use a person as an example, a young person. And one of the kidneys becomes, I'll show you maybe something like polycystic it's called. The surface gets full of all these blister-like structures. And they have to remove one. So that would be called a unilateral nephrectomy, right? Nephrectomy, removing the kidney. Unilateral, one. So if you do a unilateral nephrectomy on a young animal or person, the other kidney says, I miss you, buddy, but I'm going to grow bigger so I can make more urine. So the remaining kidney undergoes hyperplasia. Notice that one says hypoplasia. So now the remaining kidney, you could say hypertrophy too, and actually that's maybe a better word, hypertrophy, right? Hypertrophy, hypertrophy, it looks like, hypertrophy. And so it would be called unilateral compensatory hypertrophy. So unilateral, there's one left, compensatory hypertrophy. And that works in kidneys, it also works in ovaries. If an ovary is removed from a young gilt, and let's say sows or pigs ovulate, let's say 10 to 14, and you take one ovary out, the other one says, I've got to do 10 or 12 instead of my usual 6. That's interesting, isn't it? Lungs can't do it. Lungs have no place to expand. So if you remove one lung, there's no compensatory hypertrophy because it's locked in the thoracic cavity. I'm not sure about the adrenal gland. I don't know if the adrenal, if you do a unilateral adrenalectomy, if the remaining adrenal gland enlarges, you could that would be searchable, I should say. I'm sure somebody's done that. I just don't know if it does grow. My guess would be probably maybe. Okay, so we're into these terms. Agenesis basically means no growth. So the complete absence of one. And then you have aplasia. Again, aplasia and agenesis is very close to the same meaning. I'm going to go reset my camera so it records everything. Okay. Anyway, so there it is, polycystic kidneys. They have big, it just looks like it's full of blisters. Let's do a search on that one. That's always makes for dramatic pictures. Polycystic, there's all kinds of ovaries, and we'll do the kidney disease. Pretty images, full of blisters. There it is, bilateral polycystic kidney disease, and probably needs a kidney transplant. That thing is, and that doesn't develop overnight, but look at that. That's terrible because the normal should be nice and smooth, like this one here. Normal kidney, polycystic kidney. And usually there's no going back. Once it's that bad, you don't go back to normal. Too much structural damage.
So I'm guessing they wouldn't leave a kidney like that.
Well, I am not sure about that because if it's still making some urine and it's not cancerous, it's just kind of normal tissue gone bad with these blisters. If it's making some, if they can document that it's making some urine, they might leave it there because there's really, it's not going to go anyplace. I bet you it probably is, but I'm not sure. But remember, when you transplant a kidney, it's never a perfect match unless you have an identical twin, and there's always a chance of rejection. There's that major histocompatibility complex that you have to match up for people, and it's never going to be 100%. And I don't know where they draw the line where, okay, that's a good enough match for a transplant. And then they always give the person immunosuppressive drugs. So yeah, I'm not sure. If it's making urine, I have a feeling they would just leave it. But I'm not sure. I could ask somebody. Okay, so now, let's see, here it is. Okay, so that's what that is, perirenal. Remember, peri means around. Perirenal. Pseudocyst. Pseudo is, look at all these prefixes, means false. So perirenal pseudocysts. Around the kidney, you have false cysts. So external to the renal parenchyma. You guys know what parenchyma is, right? Make sure you write that down. We've had that before. The definition of parenchyma. The working, active part of any tissue. Who's doing the work? The parenchyma. The structural part of any organ is called the stroma. S-T-R-O-M-A. So there's stroma in the kidney, and there's also parenchyma. And the renal parenchyma is what's doing the work. Okay. It says cats, whatever. And then a lot of times these species specific, if you ever get into that, you should know what that species has. Like cats, remember when we did endocrinology, cats always go hyperthyroid. Usually dogs go hypo, things like that. Okay, let's do some more clicks. Yeah, question back there? No. Okay, maybe not. I thought I saw some in the peripheral. Okay, so then we've got the liver. And the liver is amazing. And it's always tucked up against the diaphragm. So the liver is like the most cranial portion of the abdominal cavity, tucked up against the diaphragm. And there's lobes in the liver. And I think in this place here, they talk about how you can remove lobes and transplant it to somebody else, and some of those lobes regenerate. Now, that's kind of interesting. And sometimes people don't like the word regenerate, but you take some lobes out, give it to somebody else, and then your liver will, I use the term regenerate. This is a great diagram. This shows you basically how the liver works. So, what's the functional unit of the liver? Lobule. And this is really a lobule. It's not quite. The lobule goes all the way around. This is one part of it, but then it's just repeated. So if you look at this, remember how I said the liver has 2 afferent blood vessels? And this will show that. 2 afferent blood vessels, 1 efferent blood vessel. And then it's got a bile duct that takes bile out. And it also has a lymph vessel going out. So there's 3 vessels that carry fluid away from the liver, right? Can you name the 3 vessels that carry fluid away from the liver? The hepatic vein, the lymph vessel, and then the bile duct, right? So look at all the things that the livers make. And I said the liver makes about 50% of all lymph made in the body in an hour, let's say. So anyway, you have this, we'll do this one first. The hepatic arteriole, that's going to be a branch off the hepatic artery. That's going to have oxygen-rich blood, right? Arteries have oxygen-rich blood. But it's going to be relatively nutrient-poor. So that's one of the afferent vessels coming in. See that arrow there? Now here's the other afferent blood vessel. That's a blood vessel, here's a blood. Portal venule. Now remember, the second blood vessel that comes in, and it's in the video I'm sure, is the portal vein. And the portal vein is draining what? A vein usually drains something. But now you've got this vein draining something, and it's going into the liver, the intestines. So the portal vein gets broken down into venules, right? Veins. What happens is this is nutrient-rich, oxygen-poor. Just the opposite of this. So this is oxygen-rich, nutrient-poor. This is nutrient-rich, oxygen-poor. And it's both flowing in here and looking, it's mixing right in here. So the 2 afferent blood systems are mixing here, and then they get carried out the central vein, and that all gets back into the hepatic vein. Okay? So then, here is bile production. So there's certain cells that are making bile, and you know the function of bile is emulsifications of fat, right? I think the video probably talks about animals that don't have gallbladders, right? Bile is usually stored in the gallbladder. Somebody in the room, don't tell me, but somebody in the room might not have a gallbladder. It's not necessary for life. If you don't have a gallbladder, you don't eat a lot of fat at one time. You know, trim that fat off that T-bone, right? Horses, for example, don't have a gallbladder. They never eat anything fat. It's all forage, so they don't need a gallbladder, right? Anyway, so things are being processed by these cells. And then this Kupffer cell is sitting there monitoring things that are flowing by. And by the way, this is a macrophage. So what are the specialized cells that are macrophages that are connected to the blood system in the liver, and it's called the Kupffer cell. So the Kupffer cell is a special white blood cell that's fixed in the liver, and anything bacteria-wise comes in, it's going to be eaten. Because there are probably some bacteria coming from the GI tract. It's not a perfect system. There's probably some bacteria coming in the portal vein, but then look at, you got these soldiers here, Kupffer cells, that are going to phagocytize that. So that's, you know, the whole thing would be the lobule, and this is one part. Hepatocyte, that means liver cell, right? Endothelial cells, those are cells that make up blood vessels. Blood vessels are made up by cells putting together space things. Okay, there's a space of this where this is occurring here. Okay, sinusoid is just always a small area full of something. Okay, so that's a good diagram. I better go maybe back this way. Okay, so here we go. Go. Yes, sinusoid. Okay, functional. I've got to go do some more reading. So then here you got organogenesis. That means how the liver is made. It's made early in the fetal life. I suspect they're talking about humans here. Takes place from the 3rd to 8th week of embryogenesis. That just means the embryo's being formed. Okay. Fetal blood supply. Oh yeah, yeah. It's really interesting to study how blood supply in the fetus is different than blood supply after birth. And so it gets kind of complicated, but there are some special way blood flows, and they describe it here pretty well, I think. Okay, physiology, blood supply, gallbladder, biliary flow. That means the bile flow, the synthesis. Okay. So, you know, I'm not sure if they say it here, but sometimes people say there's 500 functions of the liver. 500. And when they say that, they're talking about every little enzymatic step that occurs, okay? But for us, I wouldn't say, you know, name 20 of the functions, because then you got to get into enzymes and stuff. But make sure you know that, you know, this section here, the synthesis, what is it making? It's making a lot of things. And what's kind of neat is that the liver can make glucose out of non-carbohydrate substrates. And that's kind of interesting when somebody is starving or an animal is starving, because glucose is used by the brain and all that kind of stuff. So what's it called when the liver takes like some amino acids, and that amino acids are not a carbohydrate, right? And make glucose, which is a carbohydrate, out of that amino acid precursor. What's that whole process called? Gluconeogenesis. And that is a fantastic name because it means, neo means new, genesis always means production. So it's a production of glucose from basically a new source. And so some animals are very famous for gluconeogenesis. And one of them is like the cow. Because if the cow eats any sugar, any glucose source, it never gets that glucose. All the bacteria in the rumen say, I love glucose. So the bacteria, no matter what, you can feed a cow sugar, and that sugar will never show up in the blood because the rumen, the bacteria in the rumen eat it all up. So how does the cow have glucose for its functions? Gluconeogenesis. Very interesting. Only certain amino acids can be used for that. But make sure you read that, and there's that, you know, they've got it right there, gluconeogenesis. Made from amino acids, and where is it at? Right down here. Oh, come on, oh, here, right there. Lactate and glycerol. Okay, break down the fat, okay, livers, okay, so all kinds of things degrading. The liver plays a role, okay, yeah, blood clotting factors, yes, the liver makes a lot of blood clotting factors. I mean, if you read that, you've got everything you probably need for us. Right, okay. So now here, remember we said this earlier, in the first trimester fetus, the liver is the main source of red blood cell production. So now this is human, so the first 3 months they're saying of a human embryo, the liver is making red blood cells, and then that function is taken over by the bone marrow. Okay, cholesterol synthesis, yep, plays a role in screen bile. Okay, yeah, and we've mentioned this before, the liver also produces insulin-like growth factor 1. And what tells the liver to make that? If you had to make that little chart, on the far right, it would be the liver's making insulin-like growth factor 1, but what's the organ and the hormone that targets the liver to do that? So now we're on the left side of that table. Anybody remember that? Growth hormone from the anterior pituitary goes to the liver, and then the liver says, okay, because growth hormone tells me so, I'm going to make IGF-1. Okay, and then the liver is responsible for the breakdown of a lot of drugs that are given to animals and people, and hormones and stuff. And here's a bugaboo. Sometimes a normal recommended dose of a medicine given to an animal with poor liver function results in toxic levels of that drug in the blood. Because when usually drugs or hormones are given to people and animals, most of the time they don't do resulting blood levels, do they? They just say, oh, for your size, your body weight, here, take this pill. Because it's based on the half-life, right? Every drug has a half-life. Well, if your liver is not functioning right, the half-life is longer. Think about that. So let's say drug X, in normal cases, the half-life is 1 hour in a normal person. If you have liver dysfunction, then maybe the half-life is 2 hours. And if you take a pill, as they recommend, you might get toxic levels built up unbeknownst to anybody. And I think this happens with elderly people. They're usually given a lot of medicines, there's some interactions, and I think sometimes if they would just do follow-up and say, okay, you're going to be on that pill for the rest of your life, but in 2 weeks come back and we'll do a blood draw, and we'll see what the blood levels are of that drug, if they're in that therapeutic range. Because there's like a therapeutic range, and then below that is ineffective, but above that is toxic. So every time you give an animal an injection or you take a pill or something, they want a therapeutic range. But liver function, if it's not good, there'll be higher levels. And somebody that has a super liver, yes, you give that person a pill or animal, and the therapeutic range may not be reached because the half-life is shorter than the studies show, right? And the only way you can monitor that is have the animal or person on something X, and then come back in a couple of weeks and do a blood draw and see if we're doing what we want. And not enough of that is done. Okay, so then the liver is a depot tissue. Depot, that means it stores stuff, but it can give it back. It stores a little glycogen, so it can give it back as glucose, right? But then there's got these other things, like, and there's the first one, vitamin A. Look at, there's 1 to 2 years supply of vitamin A. Wow, that's pretty impressive. That's why those prey species out there, those wolves, when they kill a deer, the organs are the first thing that go, because that's the tastiest. Okay? And vitamin D, 1 to 4 month supply. And the interesting, I want to go back to vitamin A. Cats need that source because cats cannot eat plant sources of vitamin A and convert it to A. What's the plant source of vitamin A? Carotene. Dogs can take carotene and make vitamin A. Cats, they eat carotene, they cannot make vitamin A. That's why cats are called obligate carnivores. because vitamin A only occurs, it doesn't occur in any plant. It's found in animal juices. So, a lot of supplies here, vitamin B12, iron, copper, vitamin K. Okay, so we talked about the Kupffer cells. Notice how it says acting as a sieve for antigens carried to it via the portal system. That's coming from the gut. There's got to be some bacteria that slip into the blood vessel. And luckily, if you have a good functioning liver, that bacteria will not get into the rest of the blood supply. But if your liver's not functioning, then bacteria from your gut can appear in your blood supply and go to other body parts. Makes albumin, we already said that. Transport fatty acid, yeah, liver synthesizes, there it is, angiotensinogen, a hormone. Now the thing is, that's interesting, I'm not sure everybody would call that a hormone, right? But I've seen it called a hormone. I don't really call it a hormone, but that's okay if they do it. Raising blood pressure, liver, okay, all these enzymes. Okay, with aging and therefore any medicines are more likely to, oh, look at that. That's what I just said. Yeah, and it's really amazing how the liver can vary what you have. Okay, see you tomorrow at math. 175. The room is available over there right at 10:30. Some of us will be there at 11:30, who knows. You're adults, you can be there by yourself without an instructor.